everyone. Welcome to our chemistry class. Now, in continuing with the laws of thermodynamics, in earlier classes we have discussed the first law of thermodynamics, its consequence and the applications. Now, the first law of thermodynamics never says about the feasibility of any given process, that is, whether a process will take place or not take place. It simply says what is the heat transference. Now, this feasibility of the reaction means whether the reaction is spontaneous or non-spontaneous cannot be decided by the first law of thermodynamics alone. So to decide this spontaneity of the process, that is whether any given process, physical or chemical process, will take place or not takes place, to decide this we need to have another law of thermodynamics, that is the second law of thermodynamics. So before starting with the second law of thermodynamics, we need to have a concept of the spontaneity of the process. So let's start with the spontaneity of the process. So let's start what is the spontaneous process. After defining the spontaneous process, we'll go to what are the conditions required for being a process to be a spontaneous. So a spontaneous process is defined as any process which takes place on its own without any external help, or any process which occurs in a particular direction. That type of process is known as a spontaneous process. So the definition part says process which takes place in a particular direction on its own without external help. These types of process are known as spontaneous process. And if you look at this, all natural process, नेचर में जितने भी प्रोसेस हो रहे हैं सभी प्रोसेस स्पॉन्टेनियसली एंड सभी एक ही डायरेक्शन में स्मूथली मूव करते हैं. सो वी say why certain process are spontaneous and why certain process are non-spontaneous, they could not be decided by the thermodynamics alone. Now, as an example, spontaneous process, rusting of iron, water always flows from higher level to lower level, heat always transfers from hot body to a cold body, air always flows from high pressure to low pressure. This some examples of spontaneous process. Now the question is why this is spontaneous. Now this spontaneous or a feasible process, this is always going in a particular direction. Now since all the process which is occurring in universe are always spontaneous, now we need to define the criteria for spontaneity. So the criteria for the spontaneity is studied under two headings. First one is energy criteria and the second one is entropy or randomness. Or disorderness. this is energy criterion. Whenever we have an exothermic reaction, so we are taking an exothermic reaction. An exothermic reaction, after reaction, heat or energy is released from system to the surrounding. So the total heat content or the energy content of the system is decreased. If the energy content of the system is decreased, means the product formed after reaction will be more stabilized compared to the reactant. If the product is more stabilized than the reactant, then the reactant will always go towards the formation of product, given that the initial proper condition for reaction is being given. So those exothermic reactions, the energy content of the product is always less than the reactant. So reaction tends to flow towards the formation of product. So all exothermic reactions will always move in a particular direction. So we can say that all exothermic process should be a spontaneous process. That means tendency to acquire minimum energy. So any process, any chemical reaction or any process in which energy of the system is decreased, then the process will become spontaneous. That is tendency to acquire minimum energy. Tendency to acquire energy minimum. Now, when we say tendency to acquire minimum energy, then simply the thing that comes into my mind is exothermic process. All exothermic process, energy is decreased. So for all exothermic process, energy is decreased, means all exothermic process should be spontaneous. As I just mentioned, after the formation, energy is released. So energy content of the product is less than energy content of the reactant. तो reactant हमेशा product की तरफ move करेंगे. अगर एक ही डायरेक्शन में move कर रहे हैं, तो system is said to be spontaneous process. तो एक्सोथर्मिक के तो इस बात पता चल गया कि एक्सोथर्मिक होने से स्पॉन्टेनियस होगा. नाउ द क्वेश्चन इज अबाउट इंडोथर्मिक. अगर कोई भी रिएक्शन इंडोथर्मिक है, इट मींस you have to supply energy. After consumption of this energy or heat, reaction is taking place. The energy content of the product will always be greater than the energy content of the reactant. तो अगर energy content of the product ज़्यादा है, तो product should be less stable compared to the reactant. अगर reactant ज़्यादा stable है, now the question is why this reactant should be converted into the product? Because we have dealing with a chemical process. तो endothermic process, energy of the product is greater than reactant. So product having more energy is less stable compared to the reactant. So the process will not be as spontaneous. तो exothermic के केस में तो we can easily explain कि product energy is less than reactant, so reactants are converted into product, the more stable product. So process becomes spontaneous. But endothermic process, we have this endothermic process, means delta H is positive. So energy of product is greater than energy of a reactant. So why should endothermic process be spontaneous? But अगर हम देखेंगे तो there are number of endothermic process जो spontaneous भी है. Like for example, I'll give you a very simple example. Evaporation of liquid takes place at all temperature. So evaporation means liquid is to be converted into vapor. When liquid is to be converted into vapor, we have to supply energy and the process becomes endothermic. But this evaporation takes place at all temperature on its own, and this endothermic process is spontaneous. Similarly, we have a number of reactions in which the process is endothermic but still spontaneous. Now, so the why an endothermic process should be spontaneous? To simply look at this, we can explain by energy concept. We can say exothermic has to be spontaneous, but we cannot explain why endothermic reaction should be spontaneous. That means simply this energy term, tendency to acquire energy minimum, cannot explain the spontaneity of any given process. Now, since energy alone cannot decide the spontaneity of a process, we need to take the help of another quantity which is known as disorderness or the randomness of the system. Now, this orderness of the randomness. Now, we define this in such a way. Any given particular process, like look at this expansion of gas. Initially, gas was contained in the container. Now we open the container, gas is undergoing expansion. Now, during this expansion, the relative freedom of the gas molecules increases, or the randomness or the disorderness of the gas molecules increases. So when the system, you allow the expansion of gas, the system is moving, gas are moving from the container to the other space. That is, they are going in a spontaneous process. They are going in a particular direction. So this expansion of gas becomes a spontaneous process. Now, why this is spontaneous? Because on releasing the gas from the container, the gas molecules are moving in a particular state where the chaotic nature or the randomness or the disorderness is increased. Whenever there is an increase in the randomness or the disorderness, that is the relative freedom of the gas molecules are increased. If the relative freedom of the gas molecules are increased, we say the system is moving towards a random state. To increase in the random state or disorderness can also be used as a criterion for defining the spontaneity of the reaction. Similarly, take the case of dissolution of salt. These are crystalline compound solid. Now, in solid, the cations and anions are held together by very strong electrostatic force of attraction. When the cations and the anions are held very strongly by this electrostatic force, these ions cannot move freely from their lattice point. They can simply oscillate. But when we dissolve this solid crystal in water, these goes into the solution. They are dissociated into cations and anions, and when they goes into the solution, the cations and the anions are completely free and they are moving throughout the space without the interference from the other counter ion. So when this crystalline compound solid dissolved in water, the randomness again increases, the system becoming a spontaneous process. Similarly, look at this. Take the case of evaporation of liquid that we have just mentioned. During evaporation of liquid, so liquid is converted into vapor. So in case of vapors, the distance between the molecules are increases, so randomness again increases. So we, along with this energy, tendency to acquire maximum randomness, tendency to acquire maximum disorderness or randomness. So these again is used to define the spontaneity of the process. But there are again some process in which this tendency to acquire randomness again cannot be used to define this spontaneity. Like for example, I am giving a very specific example. We all know that we have LPG in our house. LPG, liquefied petroleum gas. Now gas is being condensed into liquid. Inside this cylinder, gas, which is a mixture of gas, hydrocarbon, is converted into liquid and is stored as liquid. Now this conversion of gas to liquid, this is a spontaneous process. Now take this spontaneous process. In this spontaneous process, the gas which was having highly random state is now converted into liquid having less randomness. But the process becomes spontaneous. That means simply this tendency to acquire maximum randomness or disorderness cannot decide the spontaneity of the process. So we have two criteria. One says tendency to acquire minimum, by use of which we cannot explain why endothermic process has to be spontaneous. Then second says tendency to acquire maximum randomness, but there are certain processes in which randomness is decreased but the process becomes spontaneous. So tendency to acquire maximum randomness cannot decide the spontaneity. Then we have to go for a combination of these two, so that tendency to acquire minimum energy and the tendency to acquire maximum randomness, combination of these two will decide whether any given process will be spontaneous or non-spontaneous. So the criterion for spontaneous, tendency to acquire minimum plus tendency to acquire maximum randomness. Now this term randomness, this is defined by another thermodynamic quantity which is known as entropy. So we are going to focus on this thermodynamic property, that is entropy. So we have a term that is entropy. Its symbol is S. S represents entropy. Now this entropy, as we have just defined, entropy is the measure of the randomness or disorderliness of the system. Measure of randomness or disorderness. So system will try to increase randomness or disorderness. Whenever there is an increase in randomness or disorderness, chances के system is in a spontaneous state of spontaneous motion. Now this randomness or disorderness can be explained like freedom of movement. Now when we sit in a class, everyone is highly in order state, highly disciplined state, because someone is imposing some restriction. Because inside a class we have a faculty, so in presence of this faculty, everyone sits in a disciplined way, everyone listens to the faculty, what the faculty is said in a very careful manner. So everyone is in a systematic way or in a disciplined way. The moment bell rings, everyone knows that class is over. So they won't listen anything to the faculty. They will say, okay, your time is over, now let me ask alone, and you will become in such a way that the disorderness or the disciplined nature will destroy. Once the disciplined nature is removed or this external restriction is removed, you are free to talk to your neighbors, you are free to move, you are free to do whatever you like. That is what we can say disorderness or randomness. So whenever there is a disorderness or randomness, the freedom will increase. If the freedom is increased, we say the system is moving towards a more probable state. To increase in freedom means increase in randomness or increase in disorderness is what equal as increase in probability. When the system was under highly restricted condition, we have a control state, a disciplined state, an order state. So in order state, Due to certain external restricted condition, the relative freedom of the particles was highly restricted. That is less probable state. So, with all chemical process, the process is going from a less probable state to a more probable state. This is the meaning of the randomness. So, randomness means more probable. More probable. More probable means more freedom. The system will always move from a less probable state to a more probable state. More probability means more freedom. That is the meaning of increase in randomness or disorderness of the system. Now this randomness or disorderness defined as S. Now this is a state function. The sum of the features of this entropy. This entropy is a state function. Now this being a state function, the change in entropy can only be defined. Absolute value cannot be defined. So therefore this, for any given process, suppose we have initial to the final state. If the system is moving from initial to final state, then the change in entropy will be equal to entropy of the final state minus entropy of the initial state. Or for a chemical process, suppose we are having a reactant is converted into the product, then entropy change will always be defined as the summation of entropies of the product minus the summation of entropies of the reactant. This is for chemical process. So simply saying, this is a state function, depends only the initial and final state and is independent of the way in which the process is going on. Second, this entropy depends on the mass of the system. That means this is an extensive quantity. So entropy is a mass dependent quantity, that is an extensive quantity. Now this entropy, mathematically this entropy is defined as this entropy S is defined as reversible heat exchange at any given temperature. So mathematical definition of entropy is reversible heat exchange at any given temperature, Q reversible by T, that is defined as the entropy. That is heat exchange reversibly. This is temperature. So at any given temperature, what is the heat exchange reversibly between system and surrounding? That is defined as the entropy mathematically. Now, this being the definition of entropy, the unit of entropy, unit is heat. Heat is defined in terms of joule, temperature, Kelvin. So this is joule per Kelvin. This is the unit of this state function known as entropy. This state function entropy increases with temperature. Entropy increases with temperature. Now, if you look at these definitions, look at this S is equal to Q reversible by T. You can say okay, by entropy is inversely proportional to temperature. No, don't look in this way. Entropy is how much heat is exchanged reversibly at any given temperature, that is defined as entropy. But if you keep on heating the substance, the kinetic energy of the molecule will increase, thermal energy will increase, the randomness of the motion will increase. So if we keep on increasing temperature, then entropy increases with temperature. So now entropy, this entropy change, now on changing physical state of the same species, entropy increases from solid to liquid, liquid to gas. Change in physical state, entropy increases from entropy of solid is less than entropy of liquid, which is less than entropy of gas, because gas molecules are highly random state. In case of solid, molecules are held by very strong electrostatic force, so the randomness is least, or these are highly disordered state. Gases are highly disordered state. Now entropy increases. Now suppose we are having a gas, so we take a gas. Now this gas is allowed to expand isothermally. During isothermal expansion of gas, the process is isothermal, temperature remaining constant. To internal energy change will be zero. For ideal gas, internal energy is a function of temperature only. So if temperature remaining constant, change in internal energy will be zero. But during this isothermal expansion of the gas, entropy will always increases. We are having expansion of gas, volume is increased. On increasing volume, the disorderness or randomness of the gas will always increases. So entropy increases during isothermal expansion of gas. So during isothermal expansion of gas, entropy increases. Simply saying, for gases on increasing volume, entropy increases. So that is, for ideal gas, entropy increases on increasing volume. Expansion of the increasing volume. If volume is increased, randomness of the gas molecules will increase. Then look at this entropy of universe. For a spontaneous process, the total entropy of the universe is always increasing. So in all naturally occurring processes, irreversible process, and all irreversible processes are spontaneous. And for this spontaneous process, all naturally occurring process, all irreversible process, total entropy should be greater than zero. That means entropy of universe is increasing. That is, for a spontaneous process, if the process is to be spontaneous process, that is irreversible or natural process, total entropy change should always be greater than zero. So this total entropy change, this means entropy of system plus surrounding plus entropy of surrounding. This total entropy should always be greater than zero. That means for all irreversible process, all naturally process, then entropy of the universe is constantly increasing. If the entropy of the universe is increasing, then the total entropy change should always be greater than zero. Now this means entropy of the system plus entropy of the surrounding should always be greater than zero. That is for a spontaneous process. For an isolated state, For an isolated system, this total entropy change may be equal to 0 or may be greater than 0. That means for an isolated system, entropy of the system will be 0 because system is completely isolated from the surrounding. That means there is no change in the entropy of the system. So entropy of the system will be 0. But outside this, that is the surrounding. So entropy of the surrounding will always be greater than 0. But so the summation may be greater than 0. So this is for isolated system. Now for a reversible process or an equilibrium state, a reversible or equilibrium, entropy is maximum. If entropy is maximum, so therefore change in entropy will be 0. But when the system tends to acquire equilibrium state or reversible state, then entropy reaches maximum value, and at that particular point change in entropy will be 0. That is for equilibrium state, when the system reaches equilibrium state. Now for a perfectly crystalline substance, for a perfectly crystalline substance, entropy at absolute 0. For a perfectly crystalline substance, entropy at absolute 0 is always 0. Now look at this. This substance is perfectly crystalline. If I say perfectly crystalline, means perfectly ordered. There is no disorderness in the system. Now for such type of substance at absolute 0 temperature, that is 0 Kelvin. Absolute 0 stands for 0 Kelvin. So at 0 Kelvin, entropy of a perfectly crystalline substance is always 0. This statement is known as third law of thermochemistry. So according to third law of chemistry, so third law of thermodynamics, not chemistry. Third law of thermodynamics, for a perfectly crystalline substance, entropy at absolute 0 is always 0. Means at absolute 0, the system is perfectly crystalline, so there is no disorderness and no randomness, so the entropy will always be 0. So these are some of the important salient features of this thermodynamic quantity known as entropy, which measures the randomness or disorderness of the system. So this disorderness or randomness is again used to define the spontaneity of a given process. So this is what we call as the entropy factor or randomness. So simply saying, in any given process, the system will always move from more ordered state to a disordered state, or highly ordered or state to a highly disordered state. So orderedness means less probable to a more probable state. Less probable means less freedom to a more freedom state. That is the concept of entropy, a state function which is used to define the spontaneity of any given process. Now we will show the calculation of entropy involving an ideal case. Now if ideal case changes state from initial to the final state, then what is the entropy change or what is the entropy involved? calculation of entropy change involving ideal case. Now we are going to take ideal case. If ideal case is undergoing change in state from initial to the final state, then what is the entropy change? Now we have an ideal case. Ideal case, initial at pressure P1, volume V1 and temperature T1. This is initial. Now is changing into the final state to P2, V2 and T2. This is final state. So for this we have to calculate the change in entropy. Now we have from first law of thermodynamics, we have delta U is equals to Q plus work done. Now this delta U, or for a small change we have said okay, du is equals to Q plus work done. This is for a finite change, this is for a small change. Now du is equals to Cv dt, Q work done is minus P external change into delta V, so we have P delta V. Now this is U is Cv delta T, work done is minus P external into delta V. For an ideal case, P external is approximately equals to T internal. Now again, now look at this. For an ideal case, P is equals to nRT by V. So using this P here, we get Cv dt is equals to Q minus nRT dV by dV. Now we divide this equation by T. So that Cv dt by T is equals to Q by T minus nR dV by dV. Now if the process is under reversible, if the process is reversibly carried out, now this change from initial to final, if this change is reversibly carried out, then we have look at this Q reversible by T is equals to Cv dt by T plus nR dV by dt. Now look at this Q reversible by T, we define this as D as change in entropy. So we have just seen the definition of entropy. Q reversibly exchanged with system and surrounding under a given temperature, that is defined as reversible entropy change. This is equals to Cv dt by T plus nR dV by dV. Now total change means we have to integrate here from initial to final temperature from T1 to T2 and volume for V1 to V2, because this process is reversible, so we have to find the result by integration. So this becomes, now look at this, delta S, that is final minus initial, so this equals to this is for n moles of gas, so we have to multiply here. N Cv ln T2 by T1 plus nR ln V2 by V1. So this is how entropy varies with temperature and volume. So entropy depends on temperature, volume as well as pressure. Entropy is a function of temperature, pressure as well as volume. This equation gives you how entropy relates to temperature and the volume of the gas. Now we can also define the relation between temperature and pressure. Now look at this. For ideal gas, we have PV is equals to nRT. So therefore V is equals to nRT by P. So involving using this volume in this equation we have, therefore look at this, V2 by V1 is equals to nR T2 by V is equals to nRT by P. So T2 by T2 into nR will cancel out, T1 by T1. So this is V2 by V1. So we have this ratio, V2 is nRT by P. So nRT, so T2 by P2 divided by P1 by P2. Now using this here we have, look at this, delta S is equals to NCV ln T2 by T1 plus nR ln V2 is T2 by T1 into P1 by P2 . So from this we have delta S is equals to NCV ln T2 by T1 plus N R ln T2 by T1 plus NR ln P1 by P2. Now look at this, we have ln T2 by T1 common hai. So NCV plus NR, this is defined as CP. So this is equals to NCP ln T2 by T1 plus NR ln P1 by P2. So this gives you the dependence of entropy with temperature and pressure. To simply say, entropy is a function of temperature, pressure and volume. And we have this Mayer's relationship यहाँ पे use किया है, Cp minus Cv is equals to R. So Cp is equals to R plus Cv, that means Ncp is equals to Ncp plus N R. So we have used this expression. So now this is how we define the entropy change. Now under various conditions we can define this entropy change. So we have this equation and this equation which shows the relationship between entropy and temperature, pressure, volume. Now look at this, if the process is adiabatic, for a adiabatic process, if the process is adiabatic, so Q is equals to 0, so therefore entropy change will always be 0 for a adiabatic process. If the process is isothermal, T1 equals to T2, so therefore look at this, take this equation. So isothermal change, we have this relationship. So delta S will be equals to NR, because T2 by T1 comes out to be 1, so log 1 is 0, so this term comes out to be 0, so this is NR ln V2 by V1. Or look at this equation, again look at this, we have temperature, T2 by T1 is 0, sorry 1, so log 1 is 0, so again this is equals to NR ln P1 by P2. If the process is isochoric, means volume constant, so V1 equals to V2, so we have this equation involving volume, so therefore delta S, change in entropy, will be equals to NCV ln T2 by T1, so V2 by V1 is 1, so log 1 is 0, so this term comes out to be 0. But if the process happens to be isobaric, isobaric. If the process is isobaric, then P1 equals to P2. So therefore delta S is equals to, this doesn't have any pressure, so we have this pressure term, so this comes out to be 0. So we have N Cp ln T2 by T1. So this is how we define entropy change for various process. But if the process happens to be cyclic, अगर ये cyclic process है, means a process in which initial state and the final states are same. If the process is moving from after a number of transformations coming back to the initial state, then the entropy change will always be 0 for a cyclic process. So this is how we calculate entropy change involving ideal case under different conditions. If both temperature pressure varies, we have to use this equation. If both temperature and volume varies during the change, then we have to use. If only we have this type of case, then we have to find entropy by use of this. This is for ideal case. But if we have a phase transition, how to find the entropy change? Entropy change for phase transition. Entropy change for phase transition. Suppose look at this, we have this solid is in equilibrium with liquid. So there is transition from solid to liquid. Now both solid and liquid begin equilibrium. This transition occurs at temperature which is known as fusion temperature or melting point. At melting point, let's say this is fusion temperature or melting temperature. Now for such type of case, then this entropy change will be defined as, this is entropy of fusion, or this is defined as enthalpy of fusion divided by transition temperature. So this is how we correlate entropy and enthalpy for phase transition. This is enthalpy change for this process is enthalpy of fusion. We can now have look at this. Liquid is in equilibrium with vapor. So liquid is converted into vapor. This is happening at boiling point. So suppose this temperature is T, that is boiling temperature. Then enthalpy of evaporation, vaporization. This is equals to enthalpy of vaporization divided by transition temperature, that is T, boiling point. Or if suppose there is change in allotropic form, look at it, sulfur rhombic form is in equilibrium with sulfur monoclinic form. This is allotropic transition. For this, delta S transition is equal to enthalpy of transition divided by transition temperature. Simply saying, if we have a phase transition, then enthalpy and entropy are related to each other. So by this equation we can find, look at this, if enthalpy and entropy is given, we can find what is the transition temperature, what is the boiling point, what is the melting point, or what is the fusion temperature. Or if these two are given, we can define enthalpy, entropy. If entropy and temperature is given, then also we can define enthalpy of fusion. This is how we define entropy change for a phase transition process. Now, having learned the concept of entropy or the randomness or disorderness, we are going to define the second law of thermodynamics, because this second law of thermodynamics was required to explain the feasibility or the spontaneity of the nature. We have explained how we can correlate spontaneity with energy as well as entropy. Now, having learned this, we are going to define the second law of thermodynamics. The second law of thermodynamics. Now this second law of thermodynamics is defined in number of ways. We will take up one by one. course. Transference of heat. Transference of heat from a cold body to a hot body is impossible without the performance of work. That means without any external agency, heat cannot be made to flow from a cold body to a hot body. Heat always flows from hot body to cold body. But if suppose its direction is to be changed, then this cannot be a reversible process. This cannot be a spontaneous process. Some external agent has to work on the system so that heat is to be transferred from cold body to a hot body. That means transference of heat from a cold body to a hot body is impossible without the performance of external work. That is one of the statement. Another statement of this second law of thermodynamics says all spontaneous process are thermodynamically irreversible. This is again means all irreversible processes are moving in a particular direction, so we say these are always spontaneous process. Another statement of this second law of thermodynamics. Third statement is entropy of universe is always increasing. Entropy of universe is always increasing during the course of a spontaneous process Entropy of universe is always increasing during the course of a spontaneous process and remains unchanged at equilibrium state. That means when during this spontaneous irreversible process, entropy of the universe is always increasing. But when the system reaches equilibrium state, entropy reaches maximum value, and the change in entropy at that equilibrium state is zero. Equilibrium does not. At equilibrium, entropy remains unchanged. Then the next statement of this second law of thermodynamics says the performance of any machine working reversibly cannot be 100% efficient. Efficiency of any machine cannot be 100% without the loss of some work. That is again second law of thermodynamics. Efficiency of any engine working reversibly cannot be 100% efficient. The efficiency of an engine working reversibly cannot be 100%. Any engine working in a cycle and is in a reversible process cannot have 100% efficiency. There must be some loss in efficiency. These are what we call as second law of thermodynamics. So in all these, look at this, we are using a term that is the randomness, that is entropy is taking into account. So this is the requirement of second law of thermodynamics. So simply first law cannot decide the spontaneity of the process, and to decide the spontaneity we have to introduce a term that is the randomness or disorderness. Taking into account disorderness and the energy of the system, we can easily define the process be spontaneous or non-spontaneous. So this is all about entropy and the spontaneity of the system.